Hello everyone. In this video, I want to do some examples because we saw on one hand, we saw the construction of a quotient of a group by a normal group, by a normal subgroup. And then we've seen homomorphisms, and then we proved that the kernel of a homomorphism is normal. So I want to see what happens when you do the quotient of the domain of a homomorphism by its kernel and see what we get. And at the same time, get some examples going on. So let me start with a very easy hom. So remember, we have a hom that goes from the integers, let's say, to, for concreteness, to z modulo 6. It sends n to n mod 6. Then this is a hom. I think we proved that this is a homomorphism. What is the kernel of phi? The kernel of phi is 6z. And what is the quotient of z modulo the kernel? So if I do z modulo its kernel, then this by definition of quotient is those cosets of 6z. So these are n plus 6z as n runs over all the integers. But then you can clearly see that, for example, the coset 1 plus 6z will be the same as 7 plus 6z. So you can break this. You can always break a quotient, or you can always break a group into a disjoint union of cosets. And in this case, the cosets that give you a disjoint union are the cosets 0 plus 6z, which is just 6, the multiples of 6, union 1 plus 6z, union all the way up to 5 plus 6z. So we have exactly 6 cosets. And then you can see right away that this is exactly what how we constructed z modulo 6. This is equivalent. It is, in fact, it's going to be isomorphic to z modulo 6 because remember, well, z modulo 6 was really just the congruence classes 0 through 5 modulo 6. And this congruence class, this is in fact what we call 0 modulo 6. All the numbers that are in that set are the numbers that are 0 modulo 6. This is the congruence class of 1 modulo 6. Every number that is in there is 1 modulo 6 up to the numbers that are 5 modulo 6. So what we got out of this is that the domain modulo the kernel is isomorphic to the image. Okay. And by the way, this what I did is more or less a bijection, but this is an isomorphism of groups. What's the structure on these cosets? Remember that the structure, how we defined from the definitions, the definition of addition on these cosets would be that if I add the coset A plus 6z plus the coset B plus 6z, I would get the coset A plus B plus 6z, which if A plus B is congruent to C modulo 6, this will be the same as the congruent as the coset C plus 6z. So the addition in the cosets, the addition here matches what the addition is in here, which means that this is an isomorphism of groups. All right, let me give you some other example, a little bit more sophisticated than this. For my second example, I want to remind you that in the previous video, we defined a hom, which is the sign of a permutation. So Sn going to mu2 to plus or minus 1, such that sigma goes to the sign of sigma, which is the parity of sigma. It's it's 1 if sigma is an even permutation, and minus 1 if sigma is an odd permutation. Remember, even means that it has an expression as an even product of transpositions, and odd means that sigma has an expression as a product of an odd number of transpositions. We prove this is a homomorphism. What is the kernel of the sign? The kernel of the sign is precisely, by definition, will be those sigmas in Sn where the sign is 1. So those are the sigmas in Sn such that sigma is even, which is in fact the definition of An. So the kernel is An. So what is the quotient of Sn by An? Now, we can actually use Lagrange's theorem to show that that quotient group, so by the way, we know that a kernel is normal, so this will be a quotient group. And by Lagrange's theorem, these actually will be the order of Sn divided by the order of An. And yes, in fact, it is Lagrange's theorem, because remember that Lagrange's theorem said that the order of Sn was the order of An times the index, and we did prove that the order of a quotient is the size of the index. Okay, so this, in this case, is 2. So the order of Sn is n factorial, the order of An is n factorial divided by 2. So this is a group of order 2. Okay, so I need actually just 2 cosets. What are the cosets? The cosets will be An itself, and then tau times An, some other element that is not in An. But if it's not in An, I can just do any permutation. So for example, I can just do 1, 2 times An. Okay, so that is a group, and it's a group of order 2. It is a group of order 2, which is generated by the coset 1, 2 of An. So because it is a group of order 2, it is isomorphic to Z modulo 2. And on the other hand, plus minus 1, it is also a group of order 2, so it is also isomorphic to Z modulo 2. Okay? And yeah, so you can see, though, that I can simply do an isomorphism now. The isomorphism is clear that in Sn modulo An, I can go to plus or minus 1 using the I can define it just term by term. This only has 2 elements, so I can say this one goes to 1, this one goes to minus 1, and that's it. Or I can do it much more generally. I can say, well, tau of this coset is going to go where? I'm just going to go send it to the sign of tau. Is that even well defined? Because, well, this coset could be represented by something else. But if it is represented by something else, it is an other element of tau An. So any other sigma that is in that coset will be, well, tau times some element of An. And what is then the sign of this other representative of that coset? This will be the sign of tau A, but the sign is a hom, so it will be the sign of tau times the sign of A, and the sign of A is 1, so this is just the same as the sign of tau. So this map is actually well defined, and it is surjective because this coset will go to minus 1, this coset goes to 1, and you can also prove that actually this is a group homomorphism, but because it's a surjective and injective, this is in fact an isomorphism of groups. What we will do in the next lecture will be to actually prove this in general, that this map is always an isomorphism, and that's what's called the first isomorphism theorem. Okay, let me do one more example for matrices. For my last example, let's take the other homomorphism that appeared um, in the previous video, which was the determinant. The determinant from GL2 down to non-zero reals is a hom. It sends a matrix to its determinant. And the kernel, in this case, what is the kernel of the determinant, is precisely those matrices that have determinant 1. So those matrices in GL2, whose determinant is exactly 1. That is normal in GL2, and it is usually called SL2, the special linear group, while GL2 is the general linear group. Okay, so what is GL2 modulo SL2? Now, this GL2 is an infinite group, SL2 is an infinite group, and the quotient is an infinite group. What is it? Well, by definition, it will be things of the form A times SL2. So the cosets are all of this form, and what I would like to get, that is a lot of cosets, and there's a lot of intersection in those cosets that will give me the same coset. So what I would like to do is to break this into a disjoint union of cosets, an infinite disjoint union of cosets, but I would like to find cosets that give me just a disjoint union of this set of cosets. So how am I going to do that? I'm going to show you something first. So note that what this is saying is each coset is a matrix times any other matrix in SL2. So what I'm going to claim is that actually all that matters for A, it's what is its determinant. If I know what the determinant is, then it determines in what class it's going to land. Why is that? So if you start with a matrix A, let's let little a be its determinant. Then I can construct another matrix that has determinant A, namely A001. Okay, so what is then I'm going to do the quotient of A by A001. So I'm going to multiply by the multiplicative inverse of that. Then what is this matrix? Let's say I'm going to call it S. What do I know about this matrix? The determinant of S is the determinant of A times A001 inverse, but that is, the determinant is multiplicative, it is a hom, is the determinant of A times the determinant of A001 inverse, and the determinant of an inverse is the inverse of the determinant, so this is the determinant of A times the determinant of the matrix itself inverse. The determinant of A was A, and the determinant of that matrix was also A, but I get the inverse, so this is 1. So that means that S itself is in SL2. Great. But that also means that A times A001 inverse is a matrix in SL2. And then if I multiply on the, oh boy, I wish I had multiplied on the left. So let me just actually fix that. So I'm going to take S to be, in fact, A001 inverse times A. Therefore, A itself is, if I multiply on the left by A001, then I get A001 times S. So what I get is that A actually differs from A001 by an element in SL2. So what that tells me is that actually the coset A times SL2 is the same as the coset A001 times SL2. So what that tells me, the upshot of that calculation is that when I said that GL2, the quotient of GL2 by SL2 was this big set of cosets, each one of those actually belongs to one of these. As A runs over all the non-zero real numbers. And in fact, now that is a disjoint union because each one of those matrices has determinant exactly A. So if you are a matrix of determinant A, you are in this one. If you are a matrix of determinant something else, B, then you are in some other coset. So this is, in fact, the disjoint union over all non-zero reals of the coset that is A001 times SL2R. Okay. So now I have actually broken my GL2 modulo SL2 into a disjoint union. And now I can see that actually there is a map from GL2R modulo SL2R to R cross that sends, since I know how to break these cosets, I'm going to take, in particular, this representative of a coset and send it to the number A. And now, is this an isomorphism? Well, if I take two cosets, say C1 times C2, that will be some A1, 001 times SL2 times some other coset A2, 001 SL2. And that by how cosets multiply, that is the coset that multiplies the two matrices, but how the matrices multiply, I actually get A1, A2, 001 times SL2. So what I get out of that calculation is also that this actually respects group structure. You see that A1 times A2 over the reals, it is A1, A2, and the cosets that correspond to A1 and A2 corresponds to the coset that corresponds to A1 times A2. So this is, in fact, an isomorphism. And now we've concluded that in the map determinant, the domain modulo the kernel is also isomorphic to the image, to R star. So the fact that this is an isomorphism is another example of a much more general theorem, which is the first isomorphism theorem, which we will prove next, that if I have any HOM, let's say that is surjective or non-surjective, it actually doesn't matter. But as long as it's a HOM, then we always have that G modulo the kernel is actually isomorphic to, maybe not H if it's not surjective, but it will be isomorphic to the image of psi. And the isomorphism is actually given by, if you have a coset, it will be sent to psi of G, which is actually what's happening here. What is this isomorphism? For any coset representative, so such as this, we are sending it to A. So this A is actually the determinant of A, which is the original homomorphism we had from the start. So this more general theorem tells you exactly what the isomorphism is and that there is an isomorphism. And this is, again, the first isomorphism theorem, which we will prove this one, and we will talk about other isomorphism theorems in the next video about groups.